A vector is a physical quantity that has both a magnitude and a direction. A physical quantity that has both magnitude and direction. A good example of a vector is displacement, velocity, and acceleration. While on the other hand, we have a scalar. A scalar is a physical quantity that has only magnitude. An example of a scalar is mass, time, distance, and speed. In 2.2, Peter stands at the front door of his house. Avogadro Street is 25 meters away from the front door. Peter walks to Avogadro Street and back to the front door of his house. So he walks to the street and then walks back again to his house. The first question, 2.2.1, what is the distance that Peter has walked? So we need to be asking ourselves, is distance a scalar or a vector? Distance is a scalar. It only has magnitude. It is defined as the total length of the path taken from one point to another. The total length of the path taken from one point to another. In our scenario, Peter goes from the house to Avogadro's Street. What is the distance from the house to Avogadro Street? That is 25 meters. And then again, he goes from the street back to the house. That is another distance of 25 meters. The key word here is distance. So the total distance that Peter has traveled will be equals to the 25 meters from the house to the street plus the other 25 meters from the street to the house, which will give us a total of 50 meters. So this is the distance that Peter has traveled. What about the displacement? Is the displacement also 50 meters? Bear in mind that the distance is a scalar and the displacement is a vector. That is 2.2.2. The question is saying, let's write Peter's final displacement. So let's just remind ourselves what displacement is. The displacement is the change in an object's position. It is not the total distance traveled or the length of the path taken. No, it is the change in the object's position. So Peter starts at his house, obviously, and then he goes to the street. From the street, he walks back to the house. So what is the change in Peter's position? Peter is exactly where he started. There is no change in his position. So the displacement, Peter's displacement in this case will be equals to 0 meters because there's no change in his position. The distance is 50 meters because the distance is defined as the length of the path taken. But the displacement is 0 meters because the displacement is defined as the change in an object's position. Let's look at 2.2.3. Is displacement a vector or a scalar? Give a reason for your answer. Well, at this point, we know that displacement is a vector. And the reason for that is because we have a magnitude for displacement and we also have a direction. If a physical quantity has magnitude and direction, then it is a vector. If it only consists of magnitude, then that's what we call a scalar. You probably know this by now, but anyway, let me just remind you. If you want to convert kilometers per hour to meters per second, you divide by 3.6. And then the other way around, if you want to convert meters per second to kilometers per hour, you multiply by 3.6. And we are going to use that to answer 3.1. The question says that let's convert 135 kilometers per hour to meters per second. Again, to convert from kilometers per hour to meters per second, you divide by 3.6. So let's go ahead and do that. 135 divided by 3.6 is equals to 37.5 meters per second. So instead of having kilometers per hour, we now have meters per second by just dividing with 3.6. Let's move to 3.2. Determine the velocity of car B while trying to avoid car A. Let's go through our scenario so we can see what is happening here. Car A, driving at 135 kilometers per hour, approaches a stationary car B. The driver of car B notices that car A is approaching him at a very high speed. The driver of car B reacted suddenly by accelerating his car from rest at 1.5 meters per second squared for 11.5 seconds. After 11.5 seconds, car B continued driving. Right, so 3.2 again, determine the velocity of car B while trying to avoid car A. We're going to use equations of motions here, but before we decide which equation we are going to use, we need to know which information we have. It is the information we have that is gonna guide us towards the right equation to use. So what do we have here? We have an acceleration of 1.5 meters per second squared. We have time, delta t, which is equals to 11.5 seconds. We have an initial velocity because we are told that the car starts moving from rest. So the initial velocity vi is equals to 0 meters per second. So you need to remember that every time when a vehicle starts moving from rest, then the initial velocity is 0 meters per second. What we are looking for is vf. We have 1, 2, 3, 4 equations of motions. So let's go ahead and find out which equation we can use. Let's look at equation 1. So in equation 1, we're looking for VF. We have VI, which is 0 meters per second. We have an acceleration and we have the time. So we need to go no further because we can see that equation 1 has all the variables we have. So let's just go ahead and use that equation. So we say that VF is equals to Vi plus A delta T is the equation we are going to use. And then the velocity final will be equals to the initial velocity, which is 0, plus the acceleration, which is 1.5. The acceleration is 1.5 meters per second squared, multiplied by the time, which is 11.5. If you put that in your calculator, you should get a final velocity of 17.25 meters per second. And this right here, it is the answer to 3.2. Let's look at 3.3. But let's take our equations of motions with us because we might need to use equations of motion in 3.3. Right. So the question is saying, how far has car B driven after 11.5 seconds? So again, let's jot down our information. We have delta t, which is equals to 11.5. We have our initial velocity, which is equals to 0. We have our final velocity, which is equals to 17.25. We're looking for delta x. Let's go to our equations of motions and see which one we're going to use. If you look at equation 1, we don't have delta x. So we cannot use that equation because how are we going to get delta x when the equation itself doesn't even have delta x? And then in equation 2, we have delta x, which is what we're looking for. And then VF, we have it. We have VI is 0. 2 is a constant and we have delta t. So as you can clearly see, we are going to use the second equation because it has the variables we have and are looking for. So every time when you're solving this kind of questions, you jot down your information and then guide it to which equation of motion you're supposed to use. So now we're going to say that delta x is equals to VF plus VI divided by 2 multiplied by delta t. So delta x will be equals to what is VF? VF is 17.25. We calculated it in the question above, plus VI, which is equals to 0. Everything divided by 2. Multiplied by delta t, which is 11.5. If you put that in your calculator, you should get delta x being equals to 99.19 meters. Well, displacement is a vector, so let's give a direction. If we agree that this is west and this is east, we can say that that is 99.19 meters to the east. Let's do the same for 3.2. Our velocity final is 17.25 meters per second to the east. That is because velocity it's a vector and not a scalar. Right, let's move to 3.4. The driver of car A suddenly hit the brakes and managed to stop after 40 meters. What acceleration does car A experience to come to a standstill after 4 seconds? Let's conceptualize. Let's try envision what is happening here. So the car A was traveling at a velocity of 37.5 meters per second to the east. So the initial velocity is 37.5 meters per second. And what is being said here in 3.4 is that in 4 seconds, the car comes to a stop. It comes to a standstill. So at 4 seconds, we have a velocity of 0 meters per second. But then at the same time, during that 4 seconds, the car covers a distance, or it has a displacement of 40 meters. So we have 40 meters here. And then this is all happening in 4 seconds. Well, I want to let you know right now that this is actually impossible. There is no way that the car can start with a velocity of 37.5. 4 seconds later, it has a velocity of 0 meters per second and have covered a distance of 40 meters in 4 seconds. It is actually impossible for that to happen. That is why if you use different formulas, you're gonna get different answers, because you can say that VF is equals to VI plus A delta T. We have VF because the car is coming to a stop after 40 meters. Our VF is equals to 0. What else do we have? We have VI. It is 37.5. We have our time, which is 4 seconds. So we can find our acceleration using this formula. But you can also say that VF squared is equals to VI squared plus 2A delta X. If you use this formula, we have VF squared, we have VI squared, we have delta X. You gotta find a different value. The last formula you can use here is delta X is equals to VI delta T plus a half A delta T squared. If you use this formula also, you're going to get a different value, because this equation doesn't make any physical sense. Acceleration is the rate of change in velocity. What are we saying? We're saying that A is equals to the change in the velocity divided by the change in time. That is 4.1. Let's look at 4.2 and 4.2.1. Use the graph to describe the motion of the car in the following sections. 4.2.1, we are interested in the section AB. We can see that at t is equals to 0, our velocity is 0 meters per second. And at t is equals to 20 seconds, our velocity is 10 meters per second. So what can we say about that? How can we describe that motion? We can say that with regards to the velocity increases from 0 to 10 meters per second in 20 seconds. And with regards to the acceleration, we can say that we have a positive constant acceleration. We have a positive and constant acceleration. As we can see in our graph, we have a straight line. If your velocity time graph is a straight line, then that acceleration is constant. In this instance, it is positive because our velocity is actually increasing. That's what we can say about the section AB. Let's look at the following equation, 4.2.2. With regards to CD. So at C, we have a velocity of 40 meters per second. At D, we have a velocity of 40 meters per second. So you can see that the velocity is not changing. So with regards to the velocity, we can say that the velocity remains constant. There is no increase or decrease in the velocity in that section. What about acceleration? What can we say about acceleration? What is the acceleration when VI is equals to VF, when velocity remains unchanged? Acceleration is equals to the change in velocity divided by the change in time. If there's no change in the velocity, then the acceleration will be 0 meters per second squared. So we can say that the acceleration is equals to 0. 4.2.3, which section are we interested in now? EF. Let's look at section EF. So at E, our velocity is 0 meters per second. At F, our velocity is 0 meters per second. With regards to velocity, we can say that the velocity is 0. This would imply that the car is at rest. The car is at rest. We started with a velocity of 0, and the final velocity is also equals to 0. So there's no movement. The car is not moving. And what can we say about the acceleration? Obviously, if there is no change in the velocity, then the acceleration will be 0 meters per second squared. Let's move to 4.3. In 4.3, the question is saying that let's calculate the acceleration of the car between D and E. The acceleration of the car between D and E. There's two ways of doing this. First of all, if you have a velocity time graph, you can use the gradient to find the acceleration. If you don't want to do that, then you can just use your equations of motion. But let's do both. Let's use the gradient first, and then we're going to move to equations of motions. If we use the gradient, what we're saying is that the gradient of a velocity time graph is equals to the acceleration. This will be V final minus V initial divided by time final minus time initial. This is the same as saying V2 minus V1 divided by T2 minus T1, which is what you do in math when you want to find the gradient. You say Y2 minus Y1 divided by X2 minus X1. This is exactly what we're going to do here. But the only difference is that our Y is velocity and our X is time. So what is the final velocity at E? That is 0 minus the initial velocity at D. That is 40 meters per second. Everything divided by T final, the time at E, that is 60 seconds, minus the time at D, it is 50 seconds. So that will be minus 50. If you put that in your calculator, you should get minus 4. But that minus is just giving us the direction. So we can conclude and say that our acceleration is 4 meters per second squared to the opposite direction. Before watching me do it, can you just pause the video and try using equations of motions to answer these questions using the approach I showed you on the previous questions. If you did that, then you should realize that we have an initial velocity of 40 meters per second, and we have a final velocity of 0 meters per second. Another thing we have is the change in time, which is equals to 60 minus 50, that is just 10 seconds. The equation that you use with these variables, if you're looking for the acceleration, is Vf is equals to Vi plus A delta T. So what is Vf? Vf is 0. What is Vi? That is 40 meters per second plus the acceleration multiplied by the time. If we take 40 to the left hand side, we're going to get minus 40 being equals to A multiplied by 10. We're going to divide both sides by 10. If we do that, we're going to get an acceleration that is equals to minus 4. Again, minus 4 is just the direction. So the acceleration is 4 meters per second squared to the opposite direction.